Hey, it's Brandon James here, welcoming you to the neverthenetwork.com Audioblog. The Audioblog gives you a way to listen to all the latest NTN notes post, so feel free to start the laundry, do the dishes, or drive to work while I fill you in on the cutting edge of IT infrastructure. You are listening to Episode 1, recorded on September 3rd, 2019, titled Locator ID Separation Protocol. The original post is located at neverthenetwork.com/notes/LISP. The Locator ID Separation Protocol, or LISP, was originally designed to decrease the size of routing tables on the internet. As the protocol matured, it made its way into the enterprise through solutions like Cisco Software Defined Access. In this article, I provide a summary of the problem LISP solves and how LISP functions. The purpose of this article isn't to cover the protocol in its entirety, but to build an awareness of how the protocol works. So let's jump right in and talk about why LISP exists. LISP was formally ratified under RFC 6830. The following quote from the RFC is the best summary for the problem LISP solves. For routing to be efficient, the address must be assigned topologically. For collections of devices to be easily and effectively managed, without the need for renumbering in response to topological change, such as that caused by adding or removing attachment points to the network or by mobility events. The address must explicitly not be tied to the topology. In a perfect world, at least from the perspective of an internet router, all IP-speaking devices would be distributed uniformly throughout the globe. ISPs would never suffer outages, so enterprises wouldn't need to multi-home their internet connections, and RFC 790 would have never existed. 37/8 might belong to Texas or Ontario instead of DEC. This would make it trivial for carriers to aggregate routes based on region. Unfortunately, this simply isn't how things work. Over time, ISPs have been forced to disaggregate due to both multi-homing and the increased demand for IP space. This is why we've ended up with over 700,000 routes and counting in internet routing tables. LISP provides a way to decrease the number of routes on the internet. So, how does it work? LISP separates location and identification by replacing IP addresses with RLOCs, or routing locators, and EIDs, or endpoint identifiers. RLOCs are assigned to routers based on region so they can be topologically aggregated. EIDs are assigned to endpoints and don't need to be topologically assigned. EIDs are only reachable through the RLOC on the edge of the LISP site where they reside. In contrast with typical IP routing, EID prefixes are not installed in the routing table. Instead, LISP uses an EID to RLOC database to locate EIDs and deliver packets. LISP can be thought of as a dynamic tunneling protocol. LISP data plane packets use IP in IP encapsulation, where the outer IP header contains the source and destination RLOCs, and the inner header contains the source and destination EIDs. As the packet enters the tunnel, the ingress tunnel router, or ITR, performs the encapsulation, and as the packet leaves the tunnel, the egress tunnel router, or ETR, performs the decapsulation. XTRs are LISP routers that can perform both functions. LISP endpoints continue to speak IP exactly like they do today. From the perspective of a LISP router, each endpoint has an EID, but from the perspective of the endpoint itself, it has an IP address. In addition, endpoints only send traffic to EIDs. The general flow for a LISP packet is 1. The endpoint sends a packet destined to an EID. 2. The LISP router receives the packet and looks up the destination EID in the EID to RLOC database. 3. The router encapsulates the packet and forwards it to the destination RLOC. And 4. The destination router decapsulates the packet and forwards it to the destination endpoint. Earlier we mentioned the EID to RLOC database, but we haven't talked about how the EID to RLOC resolution takes place. The EID to RLOC mapping service operates similarly to DNS, but instead of domain to IP mappings, it provides EID to RLOC mappings. The method used to provide mappings in the LISP beta network is called LISP Alternative Logical Topology, or LISP plus alt. RFC 6836 describes LISP plus alt in detail. There are other standards for LISP databases, and all provide a common interface for LISP routers. I'm not going to spend much time discussing the database implementation. Instead, we'll focus on the standard interface they provide. In addition to the definitions found in RFC 6830, RFC 6833 defines the map server interface and expands on the message types the interface uses. Map request and map replies are the two message types directly used to perform EID to RLOC resolution. Map requests are used to request EID to RLOC mappings, and map replies are used to provide mappings. RFC 6833 provides definitions for map resolvers and map servers. Map resolvers proxy map requests sent from ITRs and maintain a local EID to RLOC database. Map servers learn EID to RLOC mappings from authoritative ETRs and publish them to their EID to RLOC database. When a map resolver receives a map request and the mapping is in its local database, the resolver will respond with a map reply. If it's not in the database, the resolver may take a couple of different actions. If the resolver can determine the EID is non-existent, it will respond with a negative map reply. Otherwise, it will forward the map request to either an authoritative map server or ETR, which will then respond to the request directly. A few things to note about the map request and map reply message format. The map request message contains a map reply record field. This contains the EID to RLOC mapping of the source, so the ETR that receives the map request can update its cache upon receipt. In addition, the map request message contains a record count field. Multiple records may be requested in a single datagram. Additional request fields are simply added one after the other in a single map request packet. Just like it sounds, the record count field contains the number of requests in the packet. Looking at the map reply message format, note that multiple records may be returned for a single map request. When this happens, the priority and weight fields are used by the ITR to determine which RLOC to use, lower priority being preferred. In the case of a tie, the weight is used to determine how the load should be shared between RLOCs. The M priority and M weight fields are used for multicast traffic. Map requests also contain a record TTL field, which determines how long the record may be cached by an ITR or map resolver. Since we've covered a couple of LISP message types, I want to briefly go over the packets they are contained in. LISP data plane packets use IP and IP encapsulation, where the outer header contains the source and destination RLOCs, and the inner header contains the source and destination EIDs. I'm not going to go into detail on the packet format here, just note that the LISP header is sandwiched between the inner and outer IP headers. Unlike LISP data plane packets, LISP control plane packets are only sent to routable addresses, so they do not utilize IP and IP tunneling. Again, there aren't any huge takeaways here. Just note that the control plane packets don't utilize tunneling and contain LISP messages, such as the map request and map replies we discussed a minute ago. Now that we've got a basic understanding of how LISP works, let's go over some of its use cases. First, I want to look at LISP on the internet. The internet is the obvious and intended use case for LISP. LISP provides a potential solution to the exponential increase in routes on the internet. As IPv6 adoption increases, so will the size of internet routing tables. In addition, LISP could potentially extend the life of IPv4 by allowing the use of prefixes longer than /24 without carrier lock-in. When writing the LISP standard, the authors distinguish between provider-independent, or PI, and provider-assigned, or PA, addresses. Since PA addresses are assigned to service providers, they can be topologically aggregated. PI addresses, on the other hand, might be assigned to a company, university, or government, and therefore aren't necessarily aggregatable. In the case of the Internet, it would make sense to use PA space for RLOCs and PI space as EIDs. Interoperability between LISP and non-LISP sites becomes more of an issue when we look at the public Internet. RFC 6832 discusses 3 solutions to this problem. I'm not going to discuss any of them in full, but the solutions include proxy ITRs, proxy ETRs, and a form of NAT that substitutes EIDs for routable addresses. All IP networks are similar, so something useful for the Internet may also be useful for the enterprise. On the surface, this seems less true for LISP than it is for BGP. LISP provides a solution for exponential growth of routes, but Cisco ASR RP3 route processors can handle up to 8.5 million IPv4 routes. It's unlikely that many enterprises are close to that, and those that are will have the budget to run the latest and greatest hardware. Using LISP to avoid advertising routes into an enterprise core is generally going to just add needless complexity. That being said, LISP provides a way to route traffic to specific hosts without the need to advertise host routes. Since LISP has a concept of longest prefix matching, host routes take precedence over less specific routes to a subnet. This means LISP could be used for endpoint mobility across multiple sites. Note that while an endpoint would keep its IP address when moving to a new site, LISP does nothing to stretch layer 2, so it would need to be combined with something like OTV. The solution is rather complicated, so it lends itself well to software-defined networking. LISP is already being used by enterprises that have implemented Cisco SDA. SDA uses an enhanced version of LISP for control plane traffic in roughly the way I described above. SDA routers only maintain local routes and use LISP to locate endpoints on the SDA fabric. Cisco uses VXLAN instead of LISP to encapsulate data plane traffic from endpoints so that layer 2 headers stay intact. It's possible that other software-defined networking solutions use LISP in some way, but at this time I'm not aware of any. This concludes episode 1 of the NTN Audioblog. For more information on this topic, visit neverthenetwork.com/notes/LISP. This will take you to the original post with footnotes, comments, and an errata. If you'd like to contact me directly, my email address is brandon@neverthenetwork.com. I'd love to hear from you.